Okay, this lecture is over Module 14 of the curriculum entitled the Transport Layer. We were learning about the OSI model and going through, and here you can see in Module 8 we talked about the network layer, and that's where IP stuff happens. And then we talked about address resolution, IP version 4 addressing, IP version 6, Internet Control Message Protocol. So there were several modules here, and throw in some basic router configuration, which included IP address. So there were a number of modules that related to or were tangential to the network layer. So now we're going to layer 4, which is the transport layer. So that's what Module 14 is about. So if we move over here into the curriculum, why should I take this module? Well, the short version is to learn about the transport layer, which again is layer 4 of the OSI model, and to learn about some of the related protocols, primarily TCP and UDP, which we may have mentioned in the past. But we'll talk about those in quite a bit of detail. So the next section, what will I learn in this module? We'll learn about end-to-endpoint communications, which is the purpose of the transport layer. We'll talk about TCP and what that is. We'll talk about UDP and what that is. We'll explain again what port numbers are and how they are used with TCP and UDP. We'll talk about the connection process of establishing and tearing down connections at layer 4. We'll talk about reliability and what flow control is, and then we will compare UDP communications with TCP communications as to what their differences are. So the next part here I want to discuss, 14.1.1, is the role of the transport layer. And basically, as I said a moment ago, it is responsible for end-to-end communications. That it provides a logical communications over the network as shown in the graphic. So at layer 4, we're connecting to layer 4 on the other end, and we form a connection that we're going to send data to. And this may be a phone talking to a phone, a computer talking to a computer, a smartphone talking to smartphone, etc. So, what are the responsibilities of the transport layer? Well, the first thing is tracking or keeping track of individual conversations. So if we look down here at the graphics, we have somebody instant messaging with somebody else. We may be sending email to a mail server. We may have a web browser up looking at multiple web pages. We may be streaming video. We may be doing an online chat. So the whole purpose is to keep track of the various things that are happening on our machine to wherever they are on the remote machine. Another responsibility, since we haven't been talking about the layers of the OS model for a while, we haven't talked about PDUs. But basically, the PDU for layer 4 is segment. So it segments or breaks the data into pieces to be transmitted, and layer 4 on the other end, those segments are reassembled so that our data makes it intact from the source to the destination. And of course we do that by encapsulation, which is adding headers. So all these different chunks that are traveling over the network, it adds header information so that the chunks can make them from the source machine to the destination machine. Another responsibility is identifying the applications. And basically what that means is port numbers. So we have these logical constructs called ports. These ports have numbers, and that port is associated with a particular application. So, if we have port 110, that's pop mail, so that's listed as electronic mail. If we're doing things on port 80, we're using HTTP to look at web pages or HTML pages. If we're using 443, we're doing HTML pages, but encrypted with SSL. One of the internet chats is on port 531, for example. So the ports that applications are listing on make sure the data makes it to the correct destination. And the other responsibility is multiplexing, which means putting all these different segments from different applications onto the network. So all these are showing they had kind of coded these with different colors and shapes. These are all traveling off the machine or onto the machine, all intertwined, and it is responsibility of layer 4 to reassemble all these pieces and get it to the correct application using the port numbers. So here we have the TCP IP model. A lot of times we talk about the OSI model. But here, the transport layer, the responsibility of that are the two primary transport layer protocols are TCP for Transmission Control Protocol and UDP, which is User Datagram Protocol. So we'll talk about those in a little detail now. We'll start with TCP. TCP, Transmission Control Protocol, is what gives us what's called guaranteed in-order delivery. So what happens is, it sends packets from the source to the destination. They are transmitted and data is acknowledged so that we know whether or not it's received. If there's a certain data that is not acknowledged, it will be transmitted again after a certain amount of time. The assumption is the packets were corrupted or disappeared. Also, the segments have sequence numbers so that we can tell if they arrive in the correct or incorrect order. And the other thing too, under flow control, we will kind of control the flow of data so that the receiver is more likely to receive everything intact and in the correct order the first time through. So here we have person setting at a PC. They're using the FTP protocol, file transfer protocol, to an FTP server located on a server farm at some ISP other than ours, and we're going to send data to that. So what happens is the file is broken into segments. These segments are sent out, so there goes segment 1, 2, 3. The server gets them, and it sends back and says, hey, I acknowledge the first 3 segments, send me some more. So it goes, okay, here's 4, 5, 6. They never make it to the destination. So after a certain length of time, it says, okay, here's 4, 5, and 6 again. And this time, the network behaves, and the packets make it to the destination. So it will basically say, acknowledge 6, send 7, and then it would send 7, 8, 9. The other thing to mention is if they're sending 3 packets at a time or allowing for 3 outstanding packets, that's something called a window size of 3. which I think we will talk about later. That's guaranteed delivery. And the one thing they didn't mention is if we sent 4, 5, and 6 and it showed up 6, 4, 5, with TCP it would reorder those into the correct order. So you have guaranteed in order or correct order delivery. As compared to UDP, User Datagram Protocol, this is considered connectionless. It's going to try to deliver the packets just like it would with TCP, but there's no process to deal with packets that show up in the wrong order or don't show up at all. So they're showing a protocol called Trivial FTP, which I think we'll talk about in the next module when we talk about the application layer and application protocols. But this is a really stripped down version of FTP, and it's based on UDP, so there's no guaranteed delivery or guaranteed in order delivery. So in this case, has a file that needs to be sent. He sends 1, 2, 3, 4, 5, 6, sends all the packets, and in that case, the packets made it there, so it will acknowledge and ask to, well, actually there is no acknowledgement sent because the protocol doesn't care if the packets disappear or not, or if they show up in the wrong order. So if he sent 1, 2, 3, 4, 5, 6, and it showed up 1, 3, 2, 5, 6. So a couple packets out of order, and I think packet 4 disappeared. It's just going to do the best it can with the data. Um, 416 is basically saying make sure you use the right protocol for the right application. There's some things that have to show up intact and in the correct order to make sense. An email message would be one of those. You can't have jumbled, missing pieces of an email message. Web pages, you would want them to be intact. Database queries or database transactions, you would want them to be complete. But there's other things. The classical example for UDP is going to be streaming video. If a few packets disappear and you get black squares in your picture, I'm sure everybody at some point seen a pixelated video, or maybe it pauses or it ghosts and it kind of goes away over time. There's no way to really correct for that. So why should you use a protocol that is going to try to correct for that? So they use UDP, which we'll see is a much leaner protocol. By using UDP and streamlining it, it makes it more likely that the packets are going to show up. But if the packets disappear, oh well, they disappear. Okay, so the graphic down here is basically showing what I just talked about. 1417 is a check your understanding on the first section of Module 14, the transportation of data. So you can go through and do that on your own. So what we're going to do is we're now going to delve deeper into TCP and then UDP. So TCP is connection based. It negotiates and establishes it says permanent connection, but a connection that's going to exist during the entire communications between the source and the destination. It's going to have reliable delivery, which means all the packets are showing up. It's going to have same order or in order delivery, which means the packets are in the correct order when they're reassembled. And then it supports something called flow control. And basically flow control is telling the other end to send faster, send slower, change your window size. I think we're losing too many packets when we have a window size of 1,000. Let's move down to a window size or a number of outstanding packets to 500. Or you can actually tell it to stop for a while and then resume. So that's what flow control is. In the TCP IP header, we have 20 bytes in the header. So we have a source port, destination port, so we know what application or the packet's coming from and going to. We have a sequence number, so we can reassemble the packets. We have an acknowledgement, so if we're acknowledging packets from the other end of the communications, we can do that. We have some other fields that we'll talk about. We have this window size, we have an urgency. The header actually has a checksum to make sure that the information, just like we do for an Ethernet frame, but in this case the header of a TCP segment, make sure that it is intact. So kind of jump the gun. Down here is the explanation of these. There's some reserved bits for future use. There are control bits, which indicate the purpose or the function of the TCP segment. And I think we talked about everything else. So here in 14.2.4, they talk about protocols that use TCP, that is, they need guaranteed in-order delivery. SSH, which is interactive login. All data needs to go through. SMTP, which is a mail protocol. HTTP, which is web pages. And the example used FTP, file transfer protocol. If we were uploading or downloading files, of course, we would want to make sure they were intact. So we would use TCP for that. So that was real quick, more detailed dive into TCP. 14.2.5 is a check your understanding on this overview of TCP. And of course, you can do that on your own. Now, if we do the same thing and look in more detail at UDP, we talk about the features. The reconstruction of data doesn't reorder the packets, just whatever order they arrive in is the order the segment's going to be reassembled in. Lost segments, there's no mechanism to retransmit those. There is no session establishment. These packets just show up and are processed. And if the packets don't make it, that means the resource you were trying to access is unavailable. There's no way for it to know that there was nothing to receive these packets. So the header we saw on TCP was 20 bytes. UDP header is much more streamlined. It's 8 bytes. Basically, you have a source and destination port, so you still need to know where the packet came from and where it's going. You have a length of segment and you have a checksum, and that's all you have. So that's very streamlined. Almost a third the size of a TCP header. So we talked about all the fields. Applications that use UDP. Live video, streaming video, multimedia applications, DHCP, which is Dynamic Host Configuration Protocol, DNS, which is Domain Name Service, SNMP, which is Simple Network Monitoring Protocol. If a machine sends that its disk is more than 90% full, means to send an alert. That alert doesn't make it to the SNMP monitoring software. Well, it'll be transmitted again in, let's say, a minute. So the fact that you missed one of those updates is no big deal. Trivial FTP, which is trying to be very lean, efficient, stripped down FTP, is UDP based. Voice over IP, which is phone conversations over the internet, and video conferencing. These are things that either we don't care about possible errors, or even if we knew there was an error, there's not a whole lot we could do about it. So 14.3.5 is a check your understanding. over UDP, and as always, you can do that on your own. And we'll continue on to talk about port numbers. So when you have a conversation, you have a source port, which is on the source machine, and you have a destination port. There are different types of ports. Destination ports are often referred to as well-known port. Not always. They often are two well-known ports, such as port 80, which is HTTP, port 25, which is SMTP, etc. We'll learn these over time. The source port is, if you're on the client, is a dynamically generated random port, so that when the remote application wants to send a packet back to you, it knows how to make it to the correct application or the correct browser window on the machine, the client machine. If you have an IP and a port, so for example, if you put 192.168.1.5 colon 1305, that would be referred to as a socket. So a socket is an IP port pair separated by a colon. I don't know that they discuss it in here. Yeah, they do, socket pairs. A socket pair are two sockets that are at each end of a communication. So if you took the connection you had established and you did the socket for one machine, the socket for the other machine, and referred to those together, that would be referred to as a socket pair. So they're showing an FTP connection between a PC and a server, and at the same time we have a web browser that is also accessing that. So these communications may be happening simultaneously, and the information makes it to the correct destination using these port numbers. (1443) is talking about port number groups. I mentioned well-known ports. Well-known ports are ones that are less than 1024. You have something called registered ports that you can ask for. So well-known ports are things that occur on most machines and have from the early days, like web browsers, email clients, chat clients, remote access clients, that type of thing. Registered ports are ports that if you want to design an application and you need a port to communicate on, you can go and ask IANA organization to register a port for you. And then above 49.151 are what are referred to as private and or dynamic. And the dynamic ports are usually for the source point of communications. You generate some randomly large port number, and then you go to port 80 on a web browser, and when it sends information back, in the port number it will have the dynamically generated port so that it makes it to the correct application. Here's a big long list of well-known port numbers. Most of these, if I was teaching an in-person class and we mentioned port numbers, I might go port 25 and expect everybody to go SMTP. I go port 80, port 443, port 110, port 22, and see if the students could memorize these. I don't like memorization for the sake of memorization, but these are widely used in general in networking, and especially within the Cisco curriculum. The one thing to point out that we'll see again in Module 15 is the fact that FTP actually uses two ports. It uses one for the control of the session, and then the other one for transmitting data, port 20 and 21. So sometimes I'll go FTP, and either students won't answer or they'll answer one. I go, well, it's really a trick question because there are 2 ports that are the answer. The netstack command is a very handy command for dealing with sockets and socket pairs and port numbers. A lot of times if somebody's hacking your machine, the netstack command would be one of the first commands I would issue to try to figure out what's going on. But you're on a machine whose IP is 192.168.1.124. So it says this is the local address, so the IP, that's why it's the same. These are the ports that it is using. It's connected to this remote machine doing NetBIOS. This program is connected to this IP HTTP. So this is a web server. This is a different web server we're going to, yet another web server we're going to. And then here's ones that have names. So, we have 1, 2, 3, 4, 5 web pages open from the web browser or web browsers on the local machine. So 1445 is a check your understanding over this section on port numbers. You can do that on your own, and we will move on to the TCP communications process. So we start out with TCP server processes. So what happens is we have 2 machines. One's doing a web page request, the other's doing a mail request. Since this is a web browser, it's going to port 80. Since this is a SMTP request, it's going to port 25. So the destination ports are well-known ports. Up here we have a server. This server is, quote, listening on port 80, so it's waiting for things to connect to the web server. You also have a mail server that is listening on port 25. So this is basically talking about the requests that are being sent from the 2 client machines. So what happens is it's pointing out that the destination ports are there. The source ports are dynamically generated port numbers. And then once the request makes it to the server, we have a response coming back. So the mail server is going to say, hey, I'm port 25. I'm sending to port 51, 152. And then the source will be the well-known port that it is sending from. So it will send the packet down. Whatever mail client was running with port 51152 will get this response. Whatever program on this machine had a source port of 49152 will get this HTTP response from the server. So that's showing how the source and destination port numbers are used both directions, going to well-known ports and coming back to dynamically generated. We talked about UDP being connectionless, but we did talk about establishing and tearing down of TCP connections at the very first of this chapter. So this is showing us the process of establishing a TCP port connection. So what happens is the machine that wants to initiate the client request sends a synchronization request to the destination machine. The destination machine is going to send an acknowledgement and a synchronize request, and then the original machine is going to send back an acknowledgement. So this is called the TCP three-way handshake for establishing a connection. And then once this happens, then data is transferred back and forth between machine A and machine B. When we want to terminate or tear down, the machine that wants to terminate the connection sends a finish signal to the other machine. The second machine sends back an acknowledgement, and then it sends a finish signal as well. And then the first machine is going to send back an acknowledgement. So this is how we tear down or terminate a TCP connection. Okay, the way we go through and do these is here we have the 20 byte field of a TCP header, and down here we have control bits, and there are 6 control bits, and here are the meaning of the 6 of them. So we talked about synchronize, we talked about finish, we talked about acknowledgement. In the case of the establishing the connection, this step 2 was both a synchronize and acknowledge. So in that case, those 2 bits would be set. So there's 1 or more bits set to, in this case, tell what type of signals that we are sending back and forth. Okay, something went wrong. Okay, I suspect it probably logged me out. Helps if I type right. Okay, so instead of logging in when I started the video, I used a session that I had open earlier in the day. So it finally timed out and wanted me to re-authenticate. So I'll probably just jump back in and not worry about editing this out. So okay, so we were in module 14, section 5, 14.5.6, or 14.5.5, sorry. Okay, so we should have a video here that is approximately 7 minutes long that talks about the TCP three-way handshake. So I do think it is worth playing here in the video.
Number, or ISN, is chosen randomly at the beginning of each TCP conversation. This helps to protect against TCP connection hijacking attacks. Wireshark takes that 32-bit random number and converts it to 0. It then increments the sequence numbers and the acknowledgements from there. This makes it easier to read and follow the segments in order using the Wireshark program. Let's look at a few of the details for this initial SYN segment. We go down to the packet details window and we can see sequence number 0, that it's the relative sequence number. If we look at the flags, we see that the SYN bit has been set. You can see it here with a 1. In the next packet, packet number 11, the server responds to the initial synchronization segment. I'll go to the next screenshot, and now packet 11 is highlighted. The server responds with an acknowledgement acknowledging sequence number 0 and sending acknowledgement 1. So the initial sequence number with relative sequence number 0 has been incremented and acknowledgement 1 has been sent. We can see in the protocol details window acknowledgement number 1 and that it's the relative ACK number. The server has also sent its own synchronization segment, and that number is 0 since it's the initial conversation going the other way. If we look in the details window, we can see that the sequence number is 0, and that's a relative sequence number from the server to the host. If we look here at the flags, both the SYN bit and the ACK bit have both been set. If we go to the next screenshot, in packet 12, which is step 3 in the three-way handshake, host 10.1.1.1 responds with an acknowledgement or ACK. And if we look in the protocol details window, we see the acknowledgement number is 1, incrementing the server's synchronization segment by 1. You can see here that the acknowledgement bit has been set, but notice that the SYN bit has not been set. This is the final phase in the three-way handshake. Let's take a look at how the TCP connection terminates. I'll go to the next screenshot, and you can see in packet 16, the server is communicating to the host at 10.1.1.1 and has sent a segment with a finish or fin and an acknowledgement or ACK. In this segment, we have a fin and an ACK. The fin ends the conversation. The acknowledgement flag has been set since the three-way handshake was first established, and in every segment sent thereafter, the acknowledgement flag is set. You can see that in the next packet, packet number 17, the host has replied to the server with an acknowledgement acknowledging that the conversation has ended. This is a two-way handshake, a fin and an ACK and an ACK. If we look ahead in the packet list window to packet 18, you can see that host 10.1.1.1 then sends the server its own fin and acknowledgement, and then the server replies with its own ACK. So you have two-way handshakes to terminate the connection. If I go back to the previous screenshot and take a look at the protocol details or the packet details, we can see here in the TCP segment the flags. Notice the 1 for the acknowledgement and then the 1 for the finish or fin flag here that's been set. Notice that the acknowledgements went as high as number 374, indicating that these screenshots were probably generated from two separate packet captures in Wireshark. You can see in these last two screenshots how the conversation ends with two-way handshakes, a fin and an ACK, and then another one going the other way.
Okay, in that video, in addition to talking very detailed about the TCP three-way handshake, shows you the power of of Wireshark. And basically what that is like showing you the bits, decoding what the bits mean, pulling the port numbers out so it shows you the information by layer of the OSI model and does a lot of decoding. If it was port 80, it tells you that that's HTTP, so you don't have to look it up, etc. So that's a lot on the power of Wireshark was shown in that video. 14.5.6 is a check your understanding on the TCP communications process. Of course, you'll do that on your own. And we'll move on to the section that talks about reliability and flow control. So the reliability we have been talking about. This is guaranteed and in order delivery. So what they're showing us here is that we're sending packets. The packets may take different routes. So some of the packets went through kind of the top row of routers here. The other one went down to the bottom, went to this third one, and down. So the packets may take different routes for various reasons, depending upon latency, volume, routing tables, that type of thing. So we have data over here on our source computer. So segments 1, 2, 3, 4, 5, 6. And of course the segments are sent out of the computer to this first router in that order, and then they move through the network. So what happens is we received 1, 2, 6, 5, 4, 3. And basically what happens is those packets will be reordered. So everything showed up, they just showed up out of order. They will be reordered at the destination. So this video is going to show us this in a little more detailed. It is about 4 minutes and 5 seconds, so I will play that here in the lecture.
This video depicts a simplified example of TCP operations and is not necessarily a realistic depiction. TCP is a connection-oriented protocol in that a connection is established first using a three-way handshake before data is sent. Another characteristic of TCP is that it's a reliable protocol. Two things that make it reliable are sequence numbers and acknowledgements. Every TCP segment that's sent in a TCP conversation gets a sequence number. So every byte of data is numbered basically in a sequential list. This allows a receiving host to rebuild the data from the ordered numbered segments. If data arrives out of order at the receiving end, the data can be put back together in the proper order thanks to the sequence numbers. Acknowledgements come into play by helping the sender know that the data that's being sent is actually being received. The way this works is the sending host sends TCP segments in bytes, and the receiving host acknowledges bytes received by sending acknowledgements. There is a limit to the amount of data the sending host can send before it receives an acknowledgement from the receiver. This amount is called the window size. The window size is the total number of bytes sent in TCP segments that can be sent before receiving an acknowledgement. Using TCP window scaling, computers are able to achieve large window sizes of up to 1 gigabyte. So as the sending host sends bytes of data in TCP segments, the receiving host returns acknowledgements as it processes bytes received and frees up its buffers. We can see this depicted in this graphic. Let's start by reading the message from the sending host here. Start with byte number 1, I am sending 10 bytes. In this scenario, the 10 bytes is the window size. In reality, the window size would be a lot larger than 10 bytes, since today window sizes are typically 16 megabytes or larger. But this works nicely for this example. So the host is sending 10 bytes, starting with byte number 1. The receiving host, the server here, says, I received 10 bytes, starting with byte number 1. I expect byte 11 next. This is the acknowledgement. The server acknowledges it received the 10 bytes and now is expecting number 11. If we look down here, we can see that in this segment, starting with sequence number 1, 10 bytes have been sent. The receiver sends an ACK 11. Starting with 1, 10 bytes were sent, so the next sequence number it's expecting is an 11. This acknowledgement is sent back to the originating host. Now the originating host sends 10 more bytes, starting with sequence number 11. If we were to ask ourselves what would be the next ACK that the server would send back to the originating host, we would have to ask ourselves, what's the last sequence number sent? Starting with 11, 10 bytes were sent, so the last sequence number that was sent was 20, so the ACK would be an ACK 21. That's the next expected sequence number. You can see how sequence numbers and acknowledgements, including the window size, make TCP a very orderly and reliable protocol.
Okay, moving on to the next section, 1463. We're talking about TCP reliability, data loss, and retransmission. So data can disappear for a number of reasons, but usually it's a glitch in the network or some type of congestion that causes it not to show up. So the way that TCP works is when it sends a set of segments, it sets a timer, and then the timer runs, and hopefully we get an acknowledgement back from the machine that received the packets. But if we do not receive an acknowledgement and the timer expires, then it assumes that the packet's lost or there's some problem on the destination device, and it will just send the same set of data again. The thing to notice is it doesn't show the resending of the data. So it sends data 1, 2, 3, and for some reason 3 doesn't show up. So when the timer expires, it'll send 1, 2, 3 again, and I think these kind of need to be shifted a little, but it would acknowledge 3, and then we would get 4, 5, and 6 sent. So what it's doing is it's going through and acknowledging the data or not acknowledging the data, and if there's no acknowledgement, then there is a retransmit when the timer expires. So the next thing down here talks about an optional feature called selective acknowledgement. So basically what happens is it can acknowledge which segments were received, including discontinuous or not continuous. So basically, selective acknowledgement, you can say, hey, I got 3 in 5 through 10. I did not get 4. So it would send 4 again, and then it would start up with 11, 12, and then it would say, acknowledge 12, send 13, basically. So that's what selective acknowledgement is acknowledging a series of packets that you actually did receive. 1464 is a video that talks about this. It's 3 minutes and 22 seconds long, so I will play that here.
The graphic depicted in this video uses segment numbers in place of sequence numbers. TCP is a reliable protocol. It uses sequence numbers and acknowledgments to provide that reliability. But what happens when data is lost in transit? As a reliable protocol, there has to be a mechanism for resending lost data so that an entire piece of data, like a file or an image or a video, can be rebuilt from all of the segments. If we look at this animation, we can see this process in action. I'll press play. The source host here sends segment 1 and starts a timer. You can see the timer's running. The destination host receives segment 1, and since it's received segment 1, it's going to send an acknowledgement. Let's see what happens. We can see that the destination host has received segment 1, acknowledges the delivery, and is going to send an ACK2, an acknowledgement 2, requesting number 2. Why? It received 1, so it sends a request for 2 in an ACK2. So we'll see that get sent. All right, there goes the acknowledgement. The source receives the acknowledgement before the timer expires and now can send segment 2. There's segment 2. It's sent, and as you can see, the timer is started. It's going to wait to get an acknowledgement. If it doesn't receive an acknowledgement from the destination before the timer expires, it will resend segment 2. Let's see this in action. You can see the destination has not received segment 2. Since it hasn't received segment 2, it won't send an acknowledgement number 3 back to the device. It's not going to acknowledge that it received 2 and send an ACK 3 back to the source host. Let's see what happens. No acknowledgement. The timer expires. You can see here the timer expires. So what will the source host do? The source host will retransmit or resend segment 2 and restart the timer. This time, the information was received by the destination, and now it's going to send an ACK 3 or acknowledgement 3 requesting the next piece of data, which in this case would be number 3. The acknowledgement's received before the timer expires, and segment 3 is sent. Segment 3 is received, acknowledged, and a request for 4 is sent in an acknowledgement. The acknowledgement is received before the timer expires, and now the device can send segment 4. Or in this case, it's the end of the transmission. The ability of TCP to retransmit missing segments makes applications that use the TCP protocol very reliable.
Okay, the next 3 sections talk about different aspects of flow control. The first is window size. So what they're showing here is that we're sending approximately 1,500 bytes. Almost 3,000, 1460. We're waiting to get the acknowledgement back to send the next one. But in this case, if we change the window size, it is going to send less data. That's the change of window size. We also have something called the maximum segment size, which is how many bytes are going to be transmitted. It is typically how many bytes the destination can receive. So if the sender is trying to send more bytes than the destination can receive, then they will negotiate down. In this case, they negotiated a window size of 10,000 and a maximum segment size of 1460. So it will go through and basically slow down or send less traffic as they negotiate that. And then finally, we have congestion control. What happens is if it's not getting a lot of response, in this case from B, meaning a lot of things are being lost, it can change the number of packets that it's sending at any given time. For example, it was trying to send 4 segments at a time. It was losing some. Typically, this would happen for a period of time. So then it's saying, okay, let's just send 2 segments at a time instead of 4, or that many outstanding segments. So we can do that to avoid congestion. So 1468 is a check your understanding on this section on reliability and flow control, and you can do that on your own. And we will move to detailed information on UDP communications. A lot of this we've already contrasted with TCP and talked about before. UDP is low overhead. It has a very small header, almost only a third the size of TCP. It does not establish a connection. It just sends data. There is no reassembly of the packets, so it can lead to unreliability because packets are showing up out of order or possibly not showing up at all. For example, here we sent 1, 2, 3, 4, 5, 6, and it showed up as 12654. 3 disappeared. 4, 5, and 6 were in reverse order, but it's not going to have a chance to retransmit the lost packets, and the receiving machine is not going to reassemble the segments. Talking about server processes and request, this is kind of the same as UDP. We have a server or a service on a server that listens on particular ports. Here we have a DNS request and a radius request. This is to look up a IP or host name. A radius request is authentication. And what happens is it will send those, and it will send it to the well-known ports or the registered port of the services. If it makes it to the destination, great. If it doesn't, oh well. So what will happen here is this is still very similar to TCP. We have a dynamic port for the source for this DNS request on client 1. DNS is on port 53, so it's going to use that well-known port as the destination. Radius operates on 1812. So what happens is, it's going to have the destination ports of the well-known ports. It's going to have the source ports, which for the client is going to be the random dynamic port. So these will go to the server. When the server responds, it is going to the source port. I guess they're talking about destination. Destination port is going to be the randomly generated port on the client that sent it. And then the source port is going to be the well-known or registered port of the service running on the server. So this communications process and the source and destination ports is pretty much the same as TCP, but we just do not have the guaranteed in-order delivery that we have with TCP. 1475 is a check your understanding over UDP communications. You can do that on your own. And we'll move on to the last section, which is the module practice and quiz. So 1481 is a packet tracer that deals with TCP and UDP communications. I will be assigning this packet tracer, so watch for it to appear in Blackboard. You get off kind of easy in this module, a single packet tracer and no labs. That's kind of rare. 1482 is what did I learn in this module. So you should read this on your own, that it points out all the major concepts and points that we pointed out in module 14. So kind of long, but important. And then 1483 is your module quiz on layer 4, the transport layer of the OSI model. And that finishes up the lecture on module 14.